Welcome back, guys. So far we talked about the potential energy as an internal energy that drives the changes, all kinds of changes, and then we focused on the structure. So by bringing atoms together, make a molecule, and in making molecules you create many different bonds, and the bonds are made of electrons, and they have certain potential energy, depends on their distance and angles and things like that. So that is changing structure. Then I showed briefly, before I tackle it later extensively, the structure determines properties. I briefly explained some physical properties using intermolecular forces between solutes and solvents, and also properties like chemical reactivity. However, we need to talk a lot about this in the later videos. Right now we are working on structures. So whatever we do, we have to always consider the nature of the molecule that try to lower the internal energy. So the structure we talked about was atomic structures, such as the size and electronegativity as atomic properties. But also we started talking about molecular structures, and obviously their molecular properties. Then we briefly discussed intermolecular properties and chemical reactions. When we talked about molecular structure, we talked about Lewis structure and Bessemer to get the three-dimensional structure based on Lewis structure. Then we talked about a lot of different ways of drawing, such as Newman and Fisher, etc. So today we are going one step deeper, theoretically. But I'm not going to extensively discuss about theories. I'll make it really brief. Then I'll have a separate video that deals with a little more theories behind the topic, hybridization. So this eventually will give you more insight to the isomerization, between different structures without breaking bonds. Also will make you understand better for the chemical reactions. Okay, in order to study and figure out the structures using hybridization, you first have to anyway come up with a correct Lewis drawing, Lewis structure. must include lone pairs. Now that's what people forget the most, and that's the reason people messing up in determining correct type of hybridization. You know, the compound like a CH4, it's pretty easy. We've done that, so I'm not gonna repeat the explanation. This is a Lewis structure without using dots. And then we know when you apply Vesper, this turns into three-dimensional structures. And that's easy. We know now that is tetrahedral shape. That we know that the angle between the electrons in the bond have a 109.5 degree of angle. So the tetrahedral is known to have sp3 hybridization. For the meaning of the sp3, I'll have, like I said before, separate videos. And if you take another example, such as water, drawing is tricky. You must include lone pair, so that's not complete. If you draw complete Lewis structure, you will not forget the lone pairs. Then you know you have not 2 but 4 electron pairs on the oxygen. So 1 pair, 2, 3, and 4. So that makes oxygen having 4 pairs of electron. So they repel one another, obviously. So they also achieve tetrahedral arrangement. So oxygen still having tetrahedral arrangement of electrons. 2 pairs in the bonds and 2 pairs as a lone pairs. So they have roughly 109 here, and also between lone pairs slightly greater than 109. So roughly speaking, the water has also tetrahedral arrangement of the electron. Therefore, the hybridization for the oxygen is also sp3. I think I mentioned in previous video, but we don't say the water molecule has a tetrahedral shape. It's actually bent shape. Bent for the water molecule, tetrahedral arrangement for the 4 pairs of electron. So that makes water still sp3 hybridized atom. Okay, let's talk about this molecule. This molecule has 2 electrons in this sigma bond, and this one also has a sigma bond, and double bond consists of 1 sigma bond like CH bond, and the other is pi bond. Each bond still represents 2 electrons. And the molecule with the pi bond has flat shape. So I think you learned it from general chemistry that the molecule shaped up like a a piece of paper, unlike the tetrahedral shape. So those 3 bonds of sigma, they are on the plane, but the pi electrons are actually above and below the paper. And this pi bond is made of 2 p orbitals. So it is originated from these 2 p orbitals having same sign on the same side, donating 1 electron from each p orbital and sharing those 2, and having electron density in the middle, not as 2p anymore, but in the middle. So this is actually 2 p orbitals, but the red area, the shared area, has more electron density now, and that's called pi bond. The details about sigma bond and pi bond will be discussed in separate video, but let's focus on this molecule. Okay, so we noticed that there are sigma bonds and the pi bond, but is that all you have? So please remember, you have to show lone pairs. Do you have any lone pair? If you did the Lewis structure correctly and practiced enough, you know you have 2 more pairs of electron right there. So then now you see why oxygen has 6 its own electrons. So here you have 1, 2, 3, 4 its own electrons, and oxygen, out of these 2 in the sigma, 1 is oxygens, and out of these 2 in the pi, 1 is oxygens. So there are 6 electrons, and in the neutral state, oxygen is supposed to have 6 electrons, right? So it is a neutral state, although it has a partial negative charge due to the inductive effect, taking electron from the carbon, like we said before. Carbon is supposed to have for its own total 8, no more than 8. As you see, there are 2, 4, 6, and 8 total. But carbon has its own 4 electrons, 1, 2, and 1 out of this, 1 out of that, 4. So its formal charge is 0. So yeah, you have all neutral carbon and oxygen, and the hydrogen has its own 1 electron, so they're fine, they're neutral, and perfect Lewis structure. So when you have, when I showed you before, 4 electron pairs on the central atom, this is the best geometry, tetrahedral, having equal repulsions, the maximum distance possible. When you have 3, this is the best, trigonal planar, 120 degree and the flat shape. So whenever you have only 3 sigma bonds or lone pair, you should have the flat shape with a 120 degree. That's when you know you have sp2 hybridization. Which means you have carbon that looks like this, also oxygen that looks like that. So in their lowest potential energy with the minimum repelling force, you have the carbon in this model I just built. 1, 2, 3 pairs of electrons with 120 degrees and the flat shape, and the oxygen with a 1 sigma and the 2 lone pairs the flat shape. Then what about pi bond? Like I said here, pi bond is made by p orbitals. So the p orbital is up here and down there as well for the oxygen, and they share electron and create pi bond. So pi bond is not formed by hybridized orbital. Pi bond is formed by pure p orbital, original p orbital. So pi bond don't count because it's from p orbital. Therefore p orbitals don't count in the hybridization. So when you see the structure, you notice sigma bonds and lone pairs. Around the carbon you have 2 and 3 sigma bonds and no lone pair, so 3. That's when you know, oh, I need 1 s and the 2 p's, 3. Mix them up, you make sp2 orbitals. And also you know carbon in the valence shell, it has s, second shell s, and second shell p, and you mix 1 s and 2 p's, and you make 3 of the sp2 hybridized orbitals. You see there is a 1 p left. That's the p orbital right here for the carbon. So you have sp2 hybridized orbitals here, 1 and 2 and 3, but p orbital is left with a 1 electron. Then oxygen is the same. Oxygen has second shell as a valence shell and the 2s and 3 of the 2 p's, and you have only 1 sigma and 2 lone pairs, so you need 3 of them. So you mix them up, that's s and the 2 p's, so sp2s. You need 3 of them, and they are here. 1 to share with the carbon to form sigma bond, and lone pairs are in the sp2 orbitals. So this sigma bond here between carbon and oxygen is made by sp2 and sp2. And so the hybridized orbital is required or used for bonding and lone pair electrons. They're not p, which is eventually pi orbitals. Then, okay, how about this type of a bond? Well, you have to check the Lewis structure, right? So you know carbon is supposed to have 4 its own electron, and it shouldn't be more than 8 electrons around. So you see 2, 4, 6, 8. Nitrogen is supposed to have 5 electrons in the neutral state. 1, 2, 3. So you know there are 2 more. And you know when you put the 2 more, you see the 6 electrons repelling this pair. It should be located in the opposite direction of the atom, not up here, down there, and they're too close, 90 degree. So then nitrogen is neutral with 5 its own electron. It doesn't have more than 8 electrons for the second shell nitrogen. Now you're ready to determine type of hybridization you need for the carbon here and the nitrogen there. You know this carbon made 4 bonds. There are 4 pairs of electrons in the bonding. So it's tetrahedral. Then you know the angle between the electron pairs must be 109. So here the carbon has triple bond. Triple bond is made of 1 sigma and the 2 pi. And for the carbon, you have another sigma bond over here besides the one in the triple bond. So carbon had 2 bonding orbitals, so it must mix S, one of them, 1, and P, 1 of them. So it's sp hybridization is what the carbon need. Nitrogen, with a different reason, it still need sp hybridization because nitrogen has 1 bonding, 1 lone pair, which means you know the nitrogen has same type of orbitals as a second shell atom, 2s, 2 p's, x, y, and z, and you need only 2 hybridized orbitals, so you mix 1 s and 1 p out of the second shell, and you have 2 p orbitals left, and they are perpendicular, as you know. So they form 2 more pi bonds with the 2 p orbitals of the carbon. That's why you have 2 pi bonds. So the shape has to be 6 electron repelling this electron, so it should be linear, as well as here carbon 6 electrons repelling this electron, it should be linear. So this shape, besides the shape around the carbon by 3 more hydrogen with the 4 pairs tetrahedral, which is sp3 hybridized the carbon, the rest of the molecule should be linear. When you see the linear, or when you figure it is sp hybridized, you know it must be 180 degree between here and here, 180 degree. So next question is the compound with the only single bond always sp3 hybridized atoms, or is double bonded compound always sp2 hybridized, or the triple bond is always sp hybridized? So let's take a look. sp3 with a single bond. What if you have compound something like this? How would you draw the Lewis structure? Well, This carbon and this carbon, it has 4 bonds, as you see. So there's nothing else. You know, it is tetrahedral with sp3. Same for this guy. But for the central carbon, it's slightly different. So we have to draw our Lewis structures. So the carbon has 3 bonds. 3 automatically means I have, you know, a planar, trigonal planar structure. And the carbon is positive. What does that mean? It has only 3 electrons, not 4. So the total electron on the central carbon here, supposedly positive one, has 2, 4, 6. However, it has its own 3 electrons. The other belongs to the partners. So instead of 4, it has only 3, so formal charge is positive, and there is no more, right? No more lone pair, no more sigma bond. Obviously, there is no double bond, but you know, double bond is just made by the p orbital, and in this case, the p orbital is empty. There is no more electron. So out of 4, you mix these 3 for electrons to be stabilized. You made sp2. And this one is empty. So no pi bond. Just stay as a p. So how does it look like? It looks like carbon with a hydrogen, 2CH3. Those are on the plane, and the p orbital is going up and down like this, and this is empty, no electron. Obviously, these two carbon has a tetrahedral shape, so hydrogens are coming in and out, you know, sticking out of the plane, sp3. So around the carbon positive, it's flat. The angle is roughly here 120, and the hybridization for this carbon is sp2. So when you look at this molecule, oh, I have 3 bondings, no lone pairs, so sp2. You need 3 orbitals. What if you have CH3 that's negative? Then obviously you need 3 pairs in the sigma, 1 pair in the lone pair electron orbital. So it needs 4 mixed orbital. Therefore, it is sp3. What about this kind of species, you may ask? No charge, neither positive nor negative. So the carbon, central carbon, has 3 sigma bonds with for 2 electron each, and there's no lone pair. This is not lone pair. It's just a single electron, a radical. This can have either in the P or hybridized. Depends on other conditions. It's not determined. So it could be both ways. The more detail needs more background study, so I will try to avoid the details here. But you can say this can be sp3 or sp2, depends on the neighboring groups. Alright, so let's look at the case with the double bond. Is the double bond always ensuring the hybridization type to be sp2? One of the representative example is this type of compound. When you look at the terminal carbons, this has 1, 2, 3 sigma, 1 pi. So it's sp2. Meaning this orbital is sp2 from carbon, sp2 from carbon, sp2 from carbon, and there are 3 of them. So carbon is sp2 hybridized. That means it's making 3 sp2 orbitals, and for the sigma bond here, it needs s orbital of hydrogen. For this guy, same thing, but however, the central carbon has only 2 sigma bonds and 2 pi bonds. It's neutral, obviously, because of the 4 electrons possessed by the central carbon. So, you know, that out of the 4 orbitals, it only mix 2. So it's sp hybridized. Therefore, the geometry around this carbon has to be linear, while the geometry around the carbon is a trigonoplanar. And these two each make a pi bond. So this pi bond here is made by sp of the carbon, central carbon, and sp2. I'm sorry, the sigma bond, I meant. Sigma bond is made by the sp of the carbon, central carbon, sorry, and the sp2 of the terminal carbon. However, the pi bond is made by the p of the central, p of the terminal. So you see, it's not always the case. You even know from the earlier example, the compound with only single bond can be even sp2. So simple memorization will not work. For sp and other cases, there are always complication whenever there is a phenomenon called resonance. So after we learn more about theory, we will have a chance to talk about the other more advanced cases. But before finish, let me handle one more example. Okay, here's our last example of this video. How about this compound? We have to put them in the Lewis structure first. When the formula is given this way with the parentheses, what they mean is the CH3, 2 of them are bound to the sulfur, and sulfur is bound to the oxygen. So I put the sulfur in the middle, and oxygen with a minimum 1 bond to be a molecule. Then you have a CH3, minimum 1 bond. Then we consider valence electron to make it neutral, as shown here. Doesn't mean each atom is always neutral. It just means overall charge is neutral. So you see the carbons here, it has already 4 bonds with a full capacity, so no more variations possible. So it's a tetrahedral, meaning it's sp3 with a 109 degree of angle between electron pairs. Sulfur is supposed to have a total 6 of its own electron, and the maximum 6 own electron, but maximum can be 18 because it's third shell element. So that's when you lose octet rule. There are only, you know, less than 10 atoms following octet rule. So Let's count its own electron for sulfur. Don't worry about, maximum 18 yet. Sulfur has right now 1, 2, 3 its own, so we can have 2, 3 more. So that's a 6. And sulfur is neutral as it is now. And oxygen also, to be neutral, it should have 6 electrons, and there is 1, 2, 3, 4, 5. Then there is one more. Then we say, when we apply potential energy principle, because whatever you do, especially when you build a structure in the reaction or in any situation, electron try to feel most attraction if it's possible. Meaning if it doesn't make some atom having too much repulsion over having maximum electrons. So let's see, you can make them share more electron. Can you make the carbon and sulfur share more electron? Can we put this single electron of the sulfur in one of these two bonds? Then the sulfur can share electron, and that is more stable if electron feels more attraction. But that's not possible, because if you put electron here in the bonding, the sharing area, the carbon, sulfur, and they try to share to form a bond. Carbon already has 2 shared, and 6 more shared with the 3 hydrogens, so that's total 8 already. And there will be 9th electron, causing too much repulsion and raising potential energy too much. So electron should stay here. But what about with the oxygen? When you put this electron here and this one there and create another bond, let me redraw that. So yeah, this is a CH3 and CH3. You don't have to show. If you don't show, it's automatically is CH3. There you have 2 pairs left. When I see 2 pairs with a 4 electron here, they should be arranged as a trigonal planar with a 120 angle. Okay, let's focus to our newly formed bond here. Does it break any rule? We know that if it's possible, the electron here is more stable by feeling the plus charge from the center of the oxygen and the sulfur, rather than just sulfur or just oxygen holding each electron. So sulfur has a total, excuse me for losing this lone pair, total 2, 4, 6, 8, 10 electrons. Yeah, it broke the octet rule, but we said sulfur is third shell element, so it can have up to 18 electrons. They don't have to have 18. It just means it cannot have more than 18 due to the size of the shell, too much repulsion causing them not stable. So sulfur is fine, and it has 1, 2, 3, 4, 5, 6 its own electron. Total 10, 6 its own, so neutral, and it's fine with the 10, which is under 18. Oxygen has 2, 4, 5, 6 neutral, then total 2, 4, 6, 8 neutral, so this is perfect. Okay, then we can see oxygen has 1, 2, 3 pairs besides the p orbital. This is pi, but oxygen used only p orbital, which is not mixed. So the rest are mixed, creating 3. So it's sp2, having trigonal planar structure around the oxygen, flat. Does that mean sulfur is also sp2? Let's take a look. It has 1, 2, 3, and 4 bonding and lone pairs with a 1 pi bond. So that's not something we've seen before. So let's consider sulfur's case. Sulfur is third shell element. So it has 3s, 3 p's. So we needed 4 orbitals to make those 4 pairs of electrons in the bonding and the lone pair electrons in the hybridized orbital. We need 4, so sp3 we need, meaning 1, 2, 3, 4 mixed. We make 4 sp3s for this guy, this guys, these guys, these guys. Then what about pi? There's no orbital. Well, P gives, oxygen gives P, yes. But what does sulfur give to make a pi bond? Well, there's nothing else. Well, you know. I'm just assuming that you learned sigma bond, pi bond, and order of the orbitals and types of orbitals. For more details, I'll have another video. But here, you know, we have 3 d orbitals. So the d orbital is here to make a pi bond with a p. So that means S must be sp3. 1, 2, 3, and 4. One of them is lone pair. And the other 2 bound to the 2 methyl groups, and one last for the oxygen. Then oxygen gives p orbitals, p orbital to form pi bond, and S gives d orbital to make a pi bond, same shade. So around the pi bond it's not really planar. Only around the oxygen they are planar, but overall in this pi bond area, unlike carbon-carbon, carbon-oxygen we have seen before, it's not planar. So shockingly, it's tetrahedral with the 109 angle, and the hybridization type is sp3. So that's it for now, and I'll see you in the next video with the more theoretical stuff. Bye guys.